All right, welcome. Today is a crucial lesson. Today we look at how to solve quadratic equations using the zero product property. And to start off, we actually look at why in the world we do this in the first place. And there are a couple reasons, but one of the more important reasons that we look at is how our equation relates to our graph, which is what we've been exploring. And if we look at this, the first question we see in 859 is the y-intercept enough information to get a specific parabola? Now, part of my sketching here, it's not going to be perfect sketching, but if I were to draw a parabola that I was just thinking of, I could draw a parabola that comes down here and turns around and goes back up again. And it crosses through that y-intercept. But is that the only parabola that I can draw through that point? Well, no. I mean, some of you would think about I could do one that's facing the other direction if I had a negative x squared. Some of you might be like, oh, I could even go a little wider, give myself a smaller amplitude. All right, some of you say, well, I could give myself a bigger amplitude, and I could go like that there. There are an infinite number of parabolas that can all go through that one point. So 1 point is not enough to determine a parabola, in the same way that 1 point was not enough information to determine a specific line. All right, in a line, we needed 2 points. Well, in a parabola, we're going to need more than 1 point as well. But how many points is enough? Well, what about the x-intercepts? Now we got 2 points. That's like a line, right? 2 points determine a line, so maybe that's enough to determine a parabola. Well, if I have 2 x-intercepts here, I could draw a parabola that comes down through those 2 like that, but I could also draw one that comes a little steeper. I could draw one that goes a little less steep, and I could draw some that go upside down as well. I'm going off the screen there. But you get the picture that once again, we have an infinite number of parabolas that could go through 2 points. So that's not enough information. What we actually find is that we need 3 points to determine a specific parabola. Where if I have my 2 x-intercepts and a y-intercept, I could determine the very specific parabola that passes through all those. Now that's not a perfect picture of what we're looking at here. Technically, I would have a point there, 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 and there. That would be my specific parabola for these 3 points that were given to us, but initially those points weren't given to us as well. All right, so that would be the specific parabola going through those 3 points. So bottom line, how many points do you need to determine a parabola? You need 3 points to determine a parabola. All right, 3 points to determine the equation of a specific parabola. All right. That means 3 points would also be enough to graph a specific parabola if we were to go backwards. And that's what we're actually going to look at as we go into this here. We're going to see how can I go ahead and graph a parabola if I know those points. And we're going to start off with only the 2 most important points, which are the x-intercepts in this case. We're not going to focus on what the y-intercept and that 3rd point would do just yet. That'll come later. So right now, I just want to look at the 2 most important points are x-intercepts. And we are going to call these x-intercepts our roots. All right, they are also referred to as the roots of the parabola. And a great way to remember that is that if we have our ground here, the x-axis, I'm going to draw some grass here. On the x-axis, that is our ground, coming across the bottom here. And if you have a tree that's sitting on the ground, well, where do the roots begin? Well, the roots begin right as it crosses that ground. And as we can see here, our roots start in our nice little tree here. Great drawing. Fantastic job, Mr. Bateman. Oh, thank you. Thank you so much. All right. But our roots start right as it goes into the ground, which is at our x-axis. So that's why they refer to the roots of the parabola being the 2 points where it goes through the x-axis, meaning our x-intercepts. So we're going to focus on those 2 points specifically and how we find those. But let's start off 860 now. 860 says, all right, well, finding the x-intercepts might be a little bit of a challenge, but maybe it's similar to finding the y-intercept. We've done that before. So how would you go ahead and find the y-intercept of this equation? Well, I know that for every y-intercept in the world, the x value is always 0, and we can see that right here. We put 0 into our ordered pair. And if x is 0, well, then I can come into my equation. I can simply replace x with 0. And we will see that the y-intercept, just like a linear equation, is actually equal to the constant. Because when you put 0 in for x, our x terms just drop out of the equation, giving me negative 12. So in this case, the y-intercept for this equation is 0, negative 12. And that would be a good third point that I could use there as I graph it. But how do I find the x-intercepts? Well, in the same way that we found the y-intercept, we know that for every single x-intercept, y is equal to 0 because we're on the x-axis. So I could simply come here and I could plug 0 in for y. But then how do I solve for x? Pause the video for a moment. Try to do it on your own if you haven't done it already. At this point, if you're coming back into the video, you've tried to solve for x, and perhaps you did some unique things. Maybe you're like, okay, let's move this 12 to the other side, giving me 12 equals 2x squared plus 5x. And then maybe you were like, all right, well, I got to get rid of that x squared. Maybe I can divide by x at this point, and we get 12x equals 2x plus 5. All right, 12 over x. And now can we combine? And you try to mess with this, but you find out you get stuck. You get stuck at this point because we haven't learned how to solve an equation that has both x squared and x. Because I can't combine them, they're not like terms. Anytime I try to get rid of that x squared, I cause a problem with the other terms. We run into a problem. And this is where we have to think in a different light. Something that's going to help us think in that different light is one of our algebraic properties called the zero product property. The zero product property says if we have a product, right here, a product that is equal to 0, it's equal to 0, then either A must equal 0, or B must equal 0, or both. Which makes sense, right? I mean, just think about it. Anything times 0 is 0. So if A times B, two unknown numbers, equals 0, then one of them must have been 0. That's the only way it would make it possible. Or both of them could have been 0. Well, how does that help us here? Well, we could think about it. We've been working with quadratics recently, and right now I've got a quadratic expression here, 2x squared plus 5x minus 12, and that's equal to 0. Is there any way that I could rewrite this quadratic expression so that I have a product that is equal to 0? Well, if you thought about it just there for a moment, we've been learning how to factor. And we can factor this here. I can come in and I can say, all right, let me factor 2x squared plus 5x minus 12. And I get my diamond problem and generic rectangle set up because this is not a special case. There's no GCF because 2 and 5 are prime. And I could put my 2x squared bottom left, my negative 12 top right, multiply those to get negative 24. My sum would be 5. If this is confusing you, go back and watch my factoring video. This is not about how to teach you how to factor. We're now using that. All right, what multiplies to get negative 24 but adds to get 5? Well, we're going to have negative 3 and positive 8. That gives me negative 3x, 8x, and I can pull out my GCF on each of these rows and columns and always double check to make sure that it multiplies back to get the correct result. Now, why did I do that? Notice I didn't write my groups yet. Why did I factor? Well, my whole goal was to try and rewrite 2x squared plus 5x minus 12 as a product. And I can now rewrite that as 0 equals 2x minus 3 as my one product and x plus 4 as my other product. Now I know that I've got a product here that is equal to 0. And according to the zero product property, if I have a product that is equal to 0, then either A is equal to 0, my first group must equal 0, or B must equal 0 to make it true. Well, let's take a look at that. That means that A, this represents A, and this represents B in this situation. All right? And that means that either 2x minus 3 must equal 0 to make this equation true, or x plus 4 must equal 0 to make this equation true. Well, those are simple equations that I can solve. I can go ahead and I can solve those. I can add 3 to both sides, giving me 2x equals 3, and I can divide by 2. All right, giving me, I'm sorry, I'm running out of room here, but that gives me x equals 3/2, otherwise known as 1.5. This one's a little bit simpler yet. I just subtract 4 from each side, giving me x equals -4. That means these are the x values of my x-intercepts. So if I'm looking to find the x-intercepts, I know that one of them is 3, 2, 0, because y was 0. And the other one is -4, 0. Those are the two x-intercepts for this parabola. Let's try it again. Let's take a look at this example. Find the x-intercepts of y equals x squared plus x plus 6. Well, once again, if I'm finding the x-intercepts, I'm finding the roots, then my y value is 0. So I start off by substituting 0 in for y. Now, once I've got this, I want to go ahead and I want to factor this. I'm actually going to do my factoring work off to the side. All right. I know I'm looking for two groups here. Well, it's just x squared. There's no GCF. It's just x squared, so I know it's going to go down to just x and x. And I know I only need a diamond problem, all right, where my product is 6 and my sum is 5. Nope, sorry, I apologize. Scratch that. My sum is 1, all right? So what multiplies to get 6 but adds to get 1? I apologize. Let me just fix this real quick. I meant to make this -6. That is my bad. I'm sorry. Some of you are looking at it going, wow, that's not factorable. Well, if it's not factorable, we'll talk about what that means actually later on in the chapter here. So my bad. So once again, I'm trying to find the x-intercepts now with this quadratic equation. Set it equals 0, and I want to factor it. And as I look at what works for this case, well, what multiplies to get 6 and adds to -6 and adds to get 1? Well, that's 3 and -2. Now, you could have done that in your head a little bit, depending on how good you are at factoring at this point. You could have gone right to this next step where I rewrite my group as x plus 3 times x minus 2. And now I have a product that equals 0. I can apply the zero product property. If x plus 3 times x plus 2 equals 0, then either x plus 3 must equal 0 or x minus 2 must equal 0. And I can solve each of those to find the value of x that would make this equation true. Finding -3 there and finding that x equals 2 here. Meaning those are the two values of x that make this equation true when y is 0, and therefore those are my two x-intercepts. All right, I get 2, 0 and -3, 0. Those are my two x-intercepts for this quadratic. Let's take a look at our next example. If you're done now, feel free to shut off the video, but let's take a look at another one. This one now involves a GCF. Let's get a little more complicated here. Once again, finding the x-intercepts, I start off with 0 equals my quadratic expression here. All right? And now I want to factor that quadratic expression. First thing of factoring is to pull out that GCF. Here I see that 2 goes into all those parts. 2 times x squared is 2x squared. 2 times 3x is 6x, and 2 times 2 is 4. I now see that I've got a just x squared special case. So x squared there, it's going to go down to just x and x. And I only need my diamond problem to figure out what multiplies to get 2 but adds to get 3. Well, that's 2 and 1, so plus 2 plus 1. Now, once I'm here and I apply my zero product property, now I've got 3 things I'm multiplying together. 2, x plus 2, and x plus 1. But again, I'm going to do the same thing. Can 2 ever equal 0? No, it can't. There's no variable there. All right, so that cannot equal 0, so I'm not even going to look at that. But I do look where I have my variables. X plus 2 could equal 0 when x is -2. Therefore, the value of -2 when substituted for x will make this equation true. And I've got my last one here, x plus 1 could equal 0 to make this whole product 0. And if I subtract 1 from each side, I find that x could equal -1 in this case. In other words, -1 is the value of x that could also make this equation true. Because if I were to plot my points, -2, 0, and -1, 0, both of those would be on my parabola, which means they make my equation true. And they are my x-intercepts for this parabola. All right, so that's how we find our x-intercepts. That partnered with what we did earlier, knowing that the y-intercept is always my constant. I could see my y-intercept here would be 0, 4. That gives me 3 points that I could now use to get a sketch of my parabola.